Disaggregated memory architecture, leveraging recent advancements in high-density, byte-addressable non-volatile memory and low-latency interconnects, provides a large memory pool shared across multiple compute nodes. However, this architecture is susceptible to more frequent memory errors due to the higher random raw bit error rate of nanoscale non-volatile memory technologies. Traditional memory error protection techniques, such as parity and chipkill correct, incur expensive storage costs, making them impractical for large-scale systems. This work introduces replication-aware memory protection, RAMP, to enhance storage efficiency of protection in data-centric applications that already rely on memory replication for performance and availability. RAMP allows applications to weaken the protection of individual replicas, reducing storage cost, while still realizing a strong protection target by relying on the collective protection conferred by multiple replicas. In disaggregated memory architectures, high raw bit error rates, RBER, in non-volatile memory, NVM, technologies like phase change memory, PCM, and resistive random access memory, ReRAM, pose significant challenges. To address these errors, this paper proposes a flexible software-defined protection architecture called Replication-Aware Memory Error Protection, RAMP. RAMP's system architecture consists of compute nodes communicating with memory nodes through a control plane and data plane. Each memory node exposes its local NVM by attaching its memory controller to the control and data plane via a network interface card. An application running on a compute node uses the control plane to dynamically configure hardware-level memory error protection at the memory nodes to achieve a target uncorrectable bit error rate, UBER, and silent data corruption, SDC, rate. The application configures memory protection methods and code strengths at the granularity of individual pages, leveraging the virtual memory page table and TLB to include protection information for each page. This information is used by the memory controller to identify the protection technique for any given memory access. Memory nodes report detectable but uncorrectable memory errors, due to compute nodes for further handling, while remaining operational and continuing to serve memory accesses to non-failed memory regions, thus improving availability. RAMP targets applications that already employ replication for performance and availability, enabling them to leverage replication to correct due errors efficiently. The implementation of the replication method is left to the application for flexibility, with only minimal requirements dictated. By doing so, RAMP provides a flexible and efficient solution for tolerating memory errors in disaggregated memory architectures. The analytical model for choosing replica protection strength in a replication-aware chipkill correct memory system aims to estimate the expected reliability and performance overhead when using available replicas to correct a due. It presents two common application-level redundancy schemes: primary backup replication and erasure coding. The primary backup replication scheme maintains a primary physical block and a sequence of N1 backup physical replica blocks, with the probability of a due calculated as the joint probability of all physical block reads to fail. Erasure coding divides a logical block into k physical blocks and recodes them into n physical replica blocks, where n greater than k, with the probability of a due as the probability to have at least nk plus 1 physical blocks failed due to a due. The model computes Catchelene failure probability, physical block failure probability, and logical block failure probability from the RBER of NVM technology. It uses the symbol notation shown in Table 1 and is applied to study trade-offs between reliability and storage overhead for a recent chipkill design achieving storage efficiency through a Twitter protection scheme. In this research, the authors present RAMP, a novel approach to efficiently tolerate memory errors in high-density NVMe-based disaggregated memory systems. The proposed method leverages replication for availability and performance, allowing applications to relax the protection strength of memory protection, thereby achieving significant savings in storage cost without compromising overall protection. The study explores three chipkill protection schemes: baseline chipkill, primary backup replication, and erasure coding. By varying the storage overhead, it is observed that both primary backup replication and erasure coding can achieve the same level of due as the original chipkill design, albeit with approximately 9% less overhead. For a target SDC rate of 10 to the power of 22, An extra 2.4% overhead is needed, bringing the storage overhead savings down to 6.6%. The results confirm the main hypothesis that weakening the protection of each individual replica can lead to lower storage overhead while relying on the combined protection conferred by multiple replicas to meet a stronger protection target. This preliminary work demonstrates the potential of RAMP in optimizing storage efficiency in NVMe SED systems, and it suggests that the approach could be beneficial with low replication factors.